All right, so we're going to go after these transfer function factors. It's going to be another video where I explain these factors. Of course, these factors have a particular form. So we saw here, I didn't necessarily say, maybe I didn't say it yet, but these are both simple zeros, both of these, this term and this term. And then these are both simple poles, okay? And then this term right here is a constant gain term. Okay, so we've got, those are the basics, but I haven't explained them yet. I want to show you that if we go over here, we have, so basically the table that's in the textbook, it separates them by magnitude and phase. And on the far left-hand side, it shows you what that factor actually looks like. I've kind of taken the liberty to just put it up here in the corner just to keep it cleaner. But basically what this is saying is if my transfer function, if I just had a transfer function, h of s, and it's equal to just a value k, some constant, right? If I were to take the magnitude of h of s, I would get that, k being just a real value, its magnitude, it's basically k plus 0j, right? I could say that it's the real part squared plus the imaginary part squared and then square rooted, and I would just get k, right? My magnitude is just k. We know for Bode plots that we plot 20 times the log of the magnitude, which in this case is k, right? And so what this is saying is that for a factor, for my transfer function of a value k or some constant, the magnitude is just 20 times the log of that constant, which is exactly what I see here. It's just a flat line. So if my k was 10, right, the log base 10 of 10 is 1, right? And that would just be a value of 20. So I'm looking at my dB's axis here, right? And if I let my k, this is my dB's, right? If I let my k value be, like I said, k is equal to 10, then I can just say, okay, 20 times the log base 10 of 10, which is just a value of 1, times 20 equals 20 dBs. So I would be right here at 20 dBs, and that would be my magnitude plot for that factor, all right? And so that we're done with constant gain. Constant gain term is very easy. It's just 20 times the log of k, whatever k is. And the phase is even easier. It's just 0 degrees, which of course we can see is it's the tan inverse of the imaginary part over the real part. The imaginary part's 0. And so if I just go in my calculator and take the tan inverse of 0, I get 0. And so 0 degrees for all values of omega, right? Of course, this is my phase. I'm looking at this is my magnitude of h in dBs. This is my phase of h in degrees. And that's what I'm looking at for a constant gain term. I'm looking at a flat line for the gain in magnitude. I'm looking at a flat line for the phase, right? So hopefully that's clear enough. I just wanted to show you where these come from. The same goes for the next one, which is the origin 0. And so they're drawing it as s to the n because they're kind of generalizing it. You can have, I could have an s squared, which is the same thing as having s times s, and the effect basically doubles because, again, of course, I'd have s times s, which the magnitude of that, when I take the log of s times s, I can say that that's equal to the log of s plus the log of s. So the effects basically double. But anyways, let's just say that my transfer function is just h of j omega equals j omega, which is, that's the same thing as saying h of s is equal to s, right? If I take the magnitude of this, magnitude of h of j omega, again, I just get a value of, there's no real part, so 0 squared plus omega squared square root is just going to give me h of j omega equals omega. Okay, and so of course we know, let me just move this out of the way, we are going to take 20 times the log of omega, and that's going to be our Bode plot magnitude. And so what happens when omega is 1? Well, when omega is 1, the log of 1 is 0. We know our log rules. So if I'm looking at my dB axis here for my magnitude, I get 0 dB at omega equals 1. What happens if I increase omega to a value of 10, right? The log base 10 of 10 is 1. So at a value of 10, which is 1 decade higher, right? I've gone up 1 decade. I have gone up to a value of 20 times the log base 10 of 10, which is 20 times 1, which is just 20. So I'm at 20 dBs. 20 dBs. And if I went up another decade, I would be at 100 here, right? And then I would be at 20 log of 100, which would be 2 times 20 or 40 dBs. And so I would go up another. And so instead of having to keep track of all this and do all this every time, someone has done this for us and has just basically let us know that all I have to know is an origin 0. If I ever see this term, just a j omega or just a straight up s, right? Because again, we're letting s go to be equal to j omega for our transfer functions for frequency response. We can just note that that magnitude is going to be crossing 0 dBs at omega equals 1, and it's going to increase at 20 dB per decade. And the phase is always going to be 90 degrees. Why? Well, of course, it's because the tan inverse of, basically there's an imaginary part but no real part, is basically saying the tan inverse of infinity. And if you take you can't plug infinity into your calculator, but if you take the tan inverse of some massive number, so 99999, I get 89.99999 degrees, which is basically 90 degrees. And so this goes to 90 degrees, and that's exactly what we see here. And as I said, if this exponent goes up, so if we had 2 of these, right, it would basically double the effect. So we would end up with 90 degrees times 2, this would be sitting at 180 degrees. And this would go to 40 dBs per decade, because instead of getting just 20 dB, I would get 20 dB plus another 20 dB when we add those two terms together. So I would end up with 40 dB per decade, and so on. And so it's not important that you derive all this every time. I just wanted to show you that that's kind of what's happening, and that's where it's coming from. Someone has just gone ahead in electrical engineering, and they have taken the time to determine this magnitude and phase behavior for all these factors, so that if we can just get our transfer function into terms of these factors, then we don't have to think that hard, and we don't have to do all this math. We just have to go to this table, figure out what these terms do, and then we can decide how to sketch our Bode plot accordingly, okay? So I'm gonna go ahead and end this video. I think it's probably gotten a little bit long, and then in the next couple videos, I'll show you the origin pole, and then the simple pole and the simple 0 behavior, because those are the 5 terms that we're kind of gonna look at as I try to wrap up this module pretty soon. But again, just noting that this is how we're finding this behavior is, of course, we're treating this as a factor, or treating it as sort of like a mini transfer function, taking the magnitude, taking the phase, and it just so happens that we can generalize the magnitude and the phase for these terms, okay? So I'm gonna go ahead and end this video right here. In the next video, we'll talk about the last 3 factors, and we're gonna kind of blow through those pretty quickly.